Imagine a Yellowstone so powerful, it reshaped the very continent. What if I told you we could travel back in time, not with a machine, but with the Earth itself, to witness these ancient cataclysms? We're about to uncover the mind-blowing scientific detective work that reveals Yellowstone's prehistoric eruptions and what those massive events can tell us about the supervolcano today. Hey buddy, picture this. You're standing in Yellowstone National Park, gazing at those bubbling geysers, the steam rising like whispers from the ground, the vibrant colors of hot springs painting the landscape in unreal hues. It's serene, almost magical. Old Faithful shooting up on cue, bison wandering like they own the place. But beneath that postcard beauty lurks a beast, a sleeping giant that's roared to life in ways that make modern volcanoes look like firecrackers. We're talking about a supervolcano, one that's exploded in the past with enough force to blanket half a continent in ash and alter global climates. Yeah, Yellowstone isn't just a park, it's a window into Earth's fiery temper. And while we keep an eye on it today with all our fancy tech, the real clues to its future, they're buried in its ancient past. Let's chat about how scientists are piecing together this explosive history, why it matters, and what it means for that what if hanging over our heads. First off, let's set the stage properly. Yellowstone's got this dual personality. On the surface, it's America's first national park, a haven for wildlife and tourists, with geothermal wonders powered by heat from way down below. But dig deeper, pun intended, and you hit the truth. This place sits atop a massive hotspot, a plume of superhot mantle rock that's been punching through the North American plate for millions of years. That hotspot has migrated over time, leaving a trail of volcanic scars across the Snake River Plain, but Yellowstone's the current hot seat. The supervolcano label? It comes from those colossal eruptions that dwarf anything we've seen in recorded history. We're not talking cute lava flows here. These are VEI 8 monsters. Volcanic Explosivity Index 8, the top of the scale, spewing out over 1,000 cubic kilometers of material each time. For perspective, that's like filling the Grand Canyon multiple times over with ash and rock. And why does this prehistoric drama matter? Because understanding the rhythm of these blasts helps us gauge if the giant's stirring again. Sure, the park's monitored 24/7, but current data only tells us the now. The ancient stuff reveals the patterns, the cycles, the warnings etched in stone. Okay, let's time travel back. Yellowstone's volcanic saga kicks off around 2.1 million years ago with the Huckleberry Ridge eruption, the granddaddy of them all. This beast unleashed about 2,450 cubic kilometers of magma, ash, and gas, creating a caldera roughly 75 kilometers wide and blanketing areas as far as the Midwest in thick layers of tuff, that's solidified volcanic ash. Imagine the scene. A massive explosion that reshaped the landscape, sent ash plumes into the stratosphere, and probably cooled the planet for years. Fast forward to 1.3 million years ago, and boom! The Mesa Falls eruption, smaller but still epic, coughing up around 280 cubic kilometers and forming another caldera. Then, the most recent big one, Lava Creek, about 640,000 years ago, with over 1,000 cubic kilometers of ejecta, carving out the current Yellowstone caldera, that's 45 by 85 kilometers. That's the depression you see today, hidden under forests and lakes, but it's a scar from pure destruction. After that, no more super eruptions, but the show's not over. Between 180,000 and 70,000 years ago, the caldera filled with rhyolitic lava flows, think thick, sticky magma oozing out in massive volumes, about 600 cubic kilometers total, along north-south vent lines. The last one, the Pitchstone Plateau flow, happened around 77,000 years ago. Since then, it's been hydrothermal explosions. Big steam blasts from overheated water, not magma, like the one in Biscuit Basin in July 2024 that tossed rocks and mud everywhere, or another in Norris Geyser Basin in April 2024. These are eruptions in the volcanic sense, but they're reminders that the system's alive and kicking. Now, how do we know all this? It's not like there were eyewitnesses scribbling notes 2 million years ago. This is where the scientific sleuthing shines. It's like CSI for volcanoes, and it's thrilling. Geologists start with fieldwork, mapping the terrain, spotting layers of ash and tuff exposed in canyons or road cuts. They've been updating these maps with modern tech, like geodatabases, to pinpoint where deposits from each eruption lie. Then comes the lab magic. Radiometric dating is key, using isotopes like argon-argon or uranium-lead to clock when the rock solidified. For instance, paleomagnetic studies look at the magnetic orientation in minerals, which flips with Earth's field reversals, helping sequence events. Whole rock and mineral chemistries analyze the composition. Elements like silica tell if it's rhyolite from Yellowstone's hotspot or something else. Recent breakthroughs amp up the excitement. In 2020, researchers uncovered even older supereruptions along the hotspot track from the Miocene era 23 to 5.3 million years ago, suggesting the system's been more active than we thought. And just this year, in 2025, a University of Utah study used advanced seismic imaging to map a deeper magma reservoir beneath the known chamber, volatile, rich, and cap-like, hinting at how these ancient blasts built up. Machine learning's even helping sift through seismic data for hidden patterns. Virginia Tech folks back in 2018 tied the origins to ancient oceanic plate fragments perturbing the mantle, sparking those early eruptions. It's all multi-technique, combining chemistry, dating, and geophysics to reconstruct the puzzle. But here's the tease. That supervolcano mystery. These big blasts seem to recur every 600,000 to 800,000 years. We're about 640,000 years past the last one, so is it due? Not really. Volcanoes don't punch clocks, and studies show the magma chamber's only 5 to 15% molten, not primed for a superblast. Yet, understanding the ancient ones helps model future risks. If another VEI-8 hits, it'd devastate the U.S., with ash fallout disrupting agriculture, air travel, and climate worldwide. Smaller eruptions or explosions? More likely. And ancient data shows patterns in buildup, like increasing earthquakes or groundswell. Speaking of which, current monitoring is top-notch, but not the whole story. The Yellowstone Volcano Observatory, YVO, runs a network of 50 seismometers catching 1,500–2,500 quakes yearly, mostly tiny from magma or fluids moving. GPS stations, tilt meters, and strain meters track deformation. The ground rises and falls inches over years as magma shifts. Gas sensors sniff for CO2 and sulfur spikes, and infrasound picks up explosions like that 2024 Norris one. Monthly updates from YVO, like September 2025's, report steady activity, no alarms. But why isn't this enough? It snapshots the present. Ancient history reveals long-term cycles. For example, basaltic flows between big eruptions hint at evolving magma systems. Without the past, we'd miss that the hotspot's slowing, or that deeper reservoirs feed the shallow ones. A 2025 study sparked debate on eruption timelines, questioning where and when the next might hit, based on refined models of past events. And preparedness? YVO's got plans for hazards, from quakes to hydrothermal blasts. But the ancient lens reminds us, Yellowstone's not due, but it's capable. So, friend, next time you're in Yellowstone or just pondering from afar, remember, that beauty hides a wild history. Scientists' detective work, mapping, dating, probing, unmasks it, turning rocks into time machines. It tells us the giant sleeps soundly for now, but knowing its past keeps us ready. What a ride, huh? Earth's got stories that'll blow your mind.